James Webb Space Telescope showed us mature, massive galaxies in very high redshifts. And according to galaxy evolution, those galaxies are supposed to be older than the universe. So that doesn't make sense, and that needs to have an explanation. So here I have an explanation to that. The explanation is not based on a theory or an assumption. It's based on a direct observation that we can all make, and it's reproducible. And it's reproducible with James Webb Space Telescope and in other telescopes all supporting the same thing. So let's see what it is. So I'll start with this deep field, and this was taken in the same, inside the footprint of Hubble Space Telescope Ultra Deep Field. And that deep field of James Webb Space Telescope did not get the same exposure as Webb's first deep field. Obviously, it's not as deep. It wasn't the first, but there's something very special in it. And what we can see is that when we annotate the galaxies to galaxies that rotate in the same direction relative to the Milky Way and in the opposite direction relative to the Milky Way, then we can see that the number of galaxies that rotate in the opposite direction relative to the Milky Way, which means clockwise, is much higher than the number of galaxies that rotate in the opposite direction relative to the Milky Way. And the probability to have that distribution by chance, according to simple binomial distribution, is about 1%. And that is very surprising. Obviously, we're expecting to see the number of galaxies more or less the same or within statistical error. What we do see is 140% more galaxies that rotate in the opposite direction relative to the Milky Way. And that probably deserves an explanation. Let's see what it is. Before we go there, very quickly on the galaxy annotation process. So the annotation was done automatically, so there's no human bias involved here or some perceptual bias or so on. It was done by a symmetric algorithm. The algorithm is mathematically symmetric, so there's also no computer bias there or machine learning bias or so and things like that. It's also explainable, so it's not based on like machine learning or deep learning voodoo that has life of its own, and it does some analysis that we don't understand. Actually, the algorithm is fairly simple, is fairly mechanical, and we can see exactly what it does. And the details are in the papers specified below. But one important thing is what's written in this orange frame is that in fact, we don't even need algorithms to do that analysis. The number of galaxies is relatively small. The difference is very high. Even a 5-year-old child looking deep in the image can see that if they know what to look for. And that makes it very simple because the analysis is simple. It's not based on some fancy statistics or some computational analysis that may have certain assumptions, and some of those analyses are not reproducible. We know what we could call the reproducibility crisis. It's not just cosmology in the entire science. Here, it's something that makes it very simple. We can see it in front of our eyes. Anyone can see it. And that makes it easier to just move on and see why that happens rather than looking for all kind of like maybe there is a statistical error there or maybe something else. We can just move on and see why that happens. And here's a map that was created back in 2022. So what we see here is a map that was created with 1.3 million galaxies by the DESI legacy software. So that's a large number of galaxies. It allows to map the difference in the number of galaxies that rotate in opposite direction in different parts of the sky. And what we can see that is in one hemisphere, there's an excessive number of galaxies rotating counterclockwise. In the opposite hemisphere, there's a higher number of galaxies rotating clockwise. And that is, you can see it's very consistent throughout the sky. That is not a statistical analysis. That is not an attempt to fit statistically into a certain model. These are direct measurements. What we can also see is that the ultra deep field is exactly in this part of the sky where we expect to see a higher number of galaxies rotating clockwise, and that's exactly what we see in the deep field I just showed. But that map was created and published back in 2022. So that was before Webb was launched. There was no way to know what those deep fields would show. And still, it made a very good prediction of what we would see here. It actually made a good prediction also for the Webb's first deep field. Webb's first deep field, you can see it's in a part of the sky that we're not expected to see a big difference between galaxies that rotate in opposite direction. And that's exactly what you see in the image. If you go to the Webb's first deep field, you're going to see that the number is almost the same, pretty close. And the ultra deep field is also close to the galactic pole. That's a very important point. And it's also consistent in many other experiments with all relevant telescopes. All telescopes show the same thing. All telescopes shows that there's a dipole axis that is formed by the galaxy, the distribution of galaxy spin directions, and that dipole axis tend to peak around the galactic pole. Let's see if here we can see it a little bit better. So these are several experiments. Many of them were done by me, not all of them. Some experiments reported by other people. And we can see that all of them, in all of these experiments, the dipole axis peaks close to the galactic pole. Maybe not exactly on it, but it's in close proximity. And if that happens, that can possibly explain why we see what we see in the deep fields. And the reason is that galaxies that rotate in the same direction relative to the Milky Way are expected to be slightly dimmer than galaxies that rotate in the opposite direction relative to the Milky Way. And if that happens, that explains why we see more galaxies that rotate clockwise in the deep field, because those galaxies are just a little bit brighter than the other galaxies, and that's why we see more of them. I mean, it's not that there are more galaxies, it's just they're brighter, so we can see more of them. So it looks like there are more galaxies. Here's the analysis based on the rotational velocity of the Milky Way. So with that analysis, we can see that we should expect a brightness difference of about 0.006 magnitude based on the 220 kilometers per second of the rotational velocity of the Milky Way. And that doesn't seem a lot, and it is not a lot, but we have to remember that the physics of galaxy rotation is still not fully understood. We don't know why and how galaxies rotate, or explain specifically the rotational velocity of galaxies, and we know it behaves in an abnormal manner. And we can explain it with dark matter, we can explain it with MOND, maybe there are other theories to explain it, but we know that something doesn't fit right with the rotational velocity of galaxies. And we still don't have a proven explanation, or dark matter might be the leading explanation. It's still not proven. We don't have a proven explanation of why that happens. But fortunately, we can test that empirically. And we can see if indeed the brightness difference fits the 0.006 magnitude. And these are some examples. That's with a Sloan Digital Sky Survey and with Hubble Space Telescopes. And both of them show that galaxies that rotate in the opposite direction relative to the Milky Way are brighter than galaxies that rotate in the same direction relative to the Milky Way. And the difference is far greater than 0.006. So the maximum theoretical difference that we are expected to see is 0.006 magnitude. The observed difference is much higher than that. And by the way, all of these data are available publicly, so you can find the links in that paper specified below. You can download the data. You can run these experiments by yourself, reproduce the results, make sure the data are clean, that everything is correct, and so on. That's another example from the DESI Legacy Survey, much higher number of galaxies. And again, it shows in both the northern galactic pole and the southern galactic pole that galaxies that rotate in the same direction relative to the Milky Way are dimmer than galaxies that rotate in the opposite direction, and the difference is much higher than 0.006 magnitude. Another example with Galaxy Zoo, just testing it, making sure that everything is consistent. That is an experiment that anyone can do in 5 minutes by going to the SDSS cast server, running a simple query, and you see that galaxies that rotate in the same direction relative to the Milky Way are much brighter than galaxies that rotate in the opposite direction. The difference is much higher than 0.006 magnitude. But what we see here is that if the rotational velocity of the Milky Way can affect the light more than it's supposed to according to what we expect, then it might also affect the redshift. And because normally, when we use the redshift model, we ignore the rotational velocity of the Milky Way. Yet the Earth is moving, so it will affect the redshift, but with 220 kilometers per second, it's supposed to be negligible. So in most redshift models, the rotational velocity of the Milky Way is ignored, and also the rotational velocity of the observed galaxies. But is it a valid assumption that we can really ignore the rotational velocity? Fortunately, we can test that. And here's an experiment with several different telescopes. There are several different experiments here, several different telescopes, both the northern galactic pole and the southern galactic pole. And we can see that in all experiments, galaxies that rotate in the opposite direction relative to the Milky Way, on average, have lower redshift than galaxies that rotate in the same direction relative to the Milky Way. Again, you can, if you look in the paper that is specified below, in that paper, you will have links, URLs to all of these data, so you can get all of these data, all the data that is shown here, and you can do these experiments by yourself, make sure that the data is clean, that everything is correct, and so on. So everything is completely reproducible here. But what we can see here is that the redshift is different based on the rotational velocity of the Milky Way and the observed galaxies. And the same thing with third-party data sets that I took from other people. I didn't, these are data sets not created, not released by me, and they still show the same, exactly the same thing. So that's the data set released by Michael Longo over a decade ago. And we can see exactly the same thing. And with Galaxy Zoo data, we can also see the same thing. The Galaxy Zoo data, the statistical significance is not as strong. And that's because the number of galaxies is really small. You have less than 300 galaxies, so you can get really good statistical significance. But the difference in the redshift is still the same distance, the same difference. But what we saw in the previous experiment is a redshift difference of 0.01, about 0.01, and that does not seem very substantial difference. It is consistent, but it's not very high difference. But what we can see here, that's an experiment done with HSC data. And HSC, that's a bigger telescope. You can go deeper in space to a little bit higher redshift galaxies. And what we can see in both the southern galactic pole and the northern galactic pole, we can see that the redshift mass increases as the redshift gets higher. So for galaxies with slightly higher redshift, the difference in the redshift or the redshift bias increases. And if that trend continues to galaxies with higher redshift, then that can explain that galaxies with very high redshift, actually it's because of bias. That's not the real redshift, but that is driven by a certain bias that is driven by the rotational velocity of the Milky Way or the movement of the Earth that is not taken into account there. So that experiment, by the way, is done with galaxies that are within 60 degrees from the galactic pole. That's because of the footprint of HSC that doesn't cover exactly the galactic pole, so we need to move a little bit off, but still the results are statistically significant, very strong, about 13,000 galaxies showing, and both ends of the galactic pole showing exactly the same thing as the other experiments. And very quickly, an experiment with the HO tension, because if the redshift is biased, maybe that leads to the HO tension, why HO tension with one supernovae is different from the CMB. And what we have here is a simple experiment using the Shears data or the Shears catalog, but just limiting it to just galaxies or 1A supernova and galaxies that rotate in the same direction relative to the Milky Way. And we can see that when we do that, then the HO drops to 69, which is within statistical error from the HO of the CMB. When using just galaxies that rotate in the opposite direction relative to the Milky Way, the HO increases, and it further increases the HO tension. So that is some indication that perhaps the HO tension is driven by the rotational velocity of the Milky Way. I have to mention that it's based on a very small number of galaxies here, as you can see. So the results are not statistically significant. So that is something to look into in the future. The statistical significance is not nearly as high as everything else that I just showed. And maybe what we see here is real. It's not just driven by the rotational velocity of the Milky Way, but maybe galaxies that rotate in opposite direction relative to the Milky Way are indeed closer to Earth compared to galaxies that rotate in the opposite, in the same direction relative to the Milky Way. And that, if that happens, that might indicate that there's a cosmological scale axis that, in coincidence, is aligned with the galactic pole in the same location in the sky as the galactic pole. Maybe it's a coincidence, and if that happens, it might be an indication for a rotating universe or black hole cosmology. I consider that possibility as less likely for some reason, but again, it's difficult to make assumptions based on that. Anything can be true here. And that's about it.